Okay, we can start on page 1. We'll just do A and C here. So write an equation of the line tangent to the graph, point 2, -28. So if I want to find equation of tangent line, I need order pair and I need slope. The order pair is already given to us, so that's nice. To find the slope, we just need to find the derivative, right? Yeah, actually, we can do part B. It's good practice with relative max, relative min. I know it says absolute min, but we can talk about what that means. Okay, so we have a curve. This is not EVT because EVT would be, yeah, they got to give you endpoints. So this is going to be over the entire course of the function. Let's just go through first derivative test and talk about what it means, for absolute minimum. Okay, so let's just find relative max, relative min, and then we can circle back to what this means. So to find relative max, relative min, we can go through first derivative test. All right. Yep, set f prime equal to 0. Make your slope sine line. Hi. You have this packet, Chris? You do, okay. I go through first derivative test, so we'll find f prime, set f prime equal to 0. GCF, 3x, we can take from each term. Go through our factoring step. So maybe star method will help. A times C, 4 times -14 is -56. So multiplies to be -56, adds up to be 1. Be 7 and 8, right?
Be -7, right?
Yeah, -7. Yeah. So 8. Let's double check this. 8 times -7 is -56. 8 minus 7 is 1. We know that's good. Eight over 4 reduces to be 2. X minus 7/4 doesn't reduce, but we can pull that 4 out in front. Okay, so here's my factor form where I can pull my critical points for my first derivative test. Solve for x, I get 0, -2,
7/4.
and 7/4. Good. Okay, 7/4 is close to 2, but we can make our slope sign line here. We want to find the slope behavior within each interval, so we can find test points to insert into the derivative function. Choose -3, choose -1, choose 1, and I'll choose 2. So all these test points gets inserted into my derivative function. Gather information about slope. So -3 would be negative, negative, negative. So 3 negatives gives me negative. I know my graph is going to be falling. -1 in for x, negative, positive, negative. 2 negatives gives me positive. Positive, positive, negative. Positive, positive, positive. So we kind of have an idea how the graph's going to look, right? The graph's going to fall, rise, relative max, fall, relative min, rise. So the graph is asking for what? Absolute minimum, right? We don't know what's the absolute minimum, but we can narrow down our choices, right? It's either at or 7/4, right? The way that the graph is behaving, we know that the graph is not going to have any points lower than this, right? I'm drawing it not in, it's not to scale because I don't know which one is lower. So, but I do know that the graph is heading up on both directions. So there's no other point that's lower than these two, right? So here we can find an absolute minimum. Now, if the graph had dipped down here and if it goes down to -infinity on one side, then we don't have an absolute minimum. But in this case, because the end behavior of the graph is both headed up, we can find absolute minimum. So we just test these. How do we test to see which one is lower? Into the original, yeah. I'm just using the calculator here. So 3 times -2 to the 4th plus -2 cubed minus 21 times -2 squared. Do the same thing with 7/4. Just jump into the end here. We see the lower of the two values is -44. So we can say absolute minimum value is -44. care about the y value here. All right, part C. Part C says find the x-coordinate of each point of inflection. So point of inflection, we have to go down to the second derivative function. Go through S for concavity. So here's my f prime. That's my first derivative. To get to the second derivative, I can go through power rule again. So 36x squared plus 6x minus 42. Okay, take out a GCF of 6. Star method. A times C is negative 42. B value is 1. Okay, multiplies to be negative 42, adds up to be 1. Let's double check it. 7 times negative 6 is negative 42. That's good. 7 minus 6 is 1. That's good. Involve those fractions there. Negative 6 over 6 becomes negative 1, so that cleans up nicely. Okay, x plus 7/6. X minus 1. Set our second derivative equal to 0. Okay, solve for x. When we do that, we find our potential points of inflection. But we can't stop here and say that these are definitely points of inflections, right? We still have to do what? Yeah, we got to put them on the sign line because we have to check to see that there's actually a change in signs before we can call these points of inflection. Right now, they're still candidates. So we find values in each subinterval to test against the second derivative function. Choose negative 2, 0, 2. Okay, negative 2 goes in for x. That's negative times negative. 2 negatives gives me positive. Now we're at the second derivative function. Test.
That's another x. The condition of x.
That's right. Yeah. If there's a 6x here, then we can say x equals 0. It's behind you. Is that your test?
Oh.
Yes. Sure. So negative times negative is positive. We know second derivative is not relative max, relative min. It's concave up, concave down. So in this case, concave up. Right, 0 in for x. Just negative, right? Positive and negative. Plug it 2. Positive times positive. Okay, so this confirms it. These candidates do end up being points of inflection because F double prime changes signs.
POI. Parentheses, 1 comma. And
Normally we would, but here the direction just says find the x coordinate.
Okay.
But if it says find the order pairs, then yeah, I will have to insert these x values back into the original function to get their y values. Okay, let's go to page 2. I'm sorry, let's do page 3. Page 2 is more of the same. Page 3 is where we can practice with our derivative graphs. Okay, the figure below shows the graph of G prime, which is the derivative of function G with domain -3 to 4. Determine the values of x where G is relative min, relative max, where the graph is concave up, concave down, and then sketch a possible graph of G. So this is where we know we're looking at the G prime graph. And we have to know how to interpret the derivative graph, right? This is not the shape of the original graph. So we can't look at this and say, oh, that looks like a relative max, a relative min, a relative max, right? I mean, that would be the case if it was the original function, but it's G prime. So we talked about how we want to kind of label our derivative graphs a little differently, right? We have to understand that the y-axis no longer represents the position of this graph here, is representing the slope values of the original graph. So we have to understand that anything above the x-axis is going to represent where my original graph is going to be rising. Even though it looks like it's rising and falling here, these are all just different variations of positive slope, right? Maybe some positive slope is steeper than others, but these are different y, these are all positive y values, right? All sitting above the x-axis. Anything below the x-axis is slope 0. Anything on the x-axis, sorry, anything below the x-axis is negative slope. Anything on the x-axis, slope 0. Okay. So let's go ahead and create our slope sine line. And we want to focus our attention on this slope 0. Right. So slope 0 is going to be what we want to place onto our derivative sine line. So what can we place on our sine line here?
0,
Mm-hmm.
2, and 4.
2 and 4. Okay. Now we're also going to include -3 as well. And the reason why is because they do give us endpoints. So it does give us, we do have a stopping and ending point. So even though -3 is not a slope 0, we're still going to place it onto our slope sine line just because we do have boundaries for this problem here. Okay. Let's not look at the rise and fall of the graph. Let's look at the location of the graph. So where is the graph located between -3 and -2.5? Above or below? Below. I know it's rising here, but you want to look at the arrow here. It's decreasing. And the rising here just means that it's a different variation of negative slope, but it's still all negative slope. Are we okay with that? All right, between negative 2.5 and 0, above the x-axis, right? You want to keep looking at the left side here as your guide, right? Don't let the rise and fall throw you off. The rise and fall is going to help us find information about our concavity, but right now we're just looking at location. Between 0 and 2, look at your arrow here below. And then between 2 and 4, above. Any questions so far? Okay, so having these arrows, I think, is very helpful because you kind of know where the graph is going to rise and fall. What do you expect at negative 2.5 and 2? Not absolute, but yeah, relative mins. Okay, and then at 0, you expect relative max, right? So you know the rise and fall is going to match more like these arrows than what you see here. Okay, so now we're just really depending on this to help us find information. Okay, so part A says find relative max, find relative min, justify your answer. So we can write our because statements just based off of the slope sign line here. So we can say relative minimum at because f prime changes sign from negative to positive. A couple things I noticed on the quiz, which I'll give back to you, is the because statements. Sometimes I took off points because students didn't quite write out the because statements I'm looking for. So sometimes I see students say they would say because sign changes. Okay, that's not good enough because you got to identify what you're referring to. You want to say f prime is changing signs. Or I would see it changes signs. Okay, so that's not good enough either. You want to label. And then also changes signs is not good enough either. You got to specify the direction of change from negative to positive. So a lot of different variations that I saw students make.
Yeah. The only time you can really just so you change signs is for POI, right?
That's right, for point inflection. Point inflection doesn't really specify, and it doesn't matter whether it's going from concave up to concave down to concave up. We don't really specify that difference, but
just when it changes.
Yeah, just when it changes. Yeah. Okay, relative minimum. Oh, sorry, max. Now we could write intervals of increase, intervals of decrease, but they're not asking for it for part A, so we can skip to part B. So part B asks, determine the value for where the graph is concave up and concave down. So now we want to pull the concavity information from this first derivative, but we don't want to look at this and think, oh, wait, that looks like a concave, concave down, concave up, concave down. This is not the original graph, so we can't rely on that shape because this is not the original graph. This is the derivative graph. But what we can do is we can create our second derivative sign line. But now we've got to pick out our points of inflection. And where do we look for points of inflection off of the derivative graph? Not the x-intercepts. It's going to be the what? Peaks and valleys. Peaks and valleys, yeah. The reason why these are points of inflections on the original graph is because your points of inflection on the original graph is where your maximum and your minimum steepness is going to occur. So the maximum minimum steepness, because this is the slope y-axis is the slope. Whatever is the highest and lowest points is going to be where your graph is actually going to experience, the biggest dip in terms of its steepness. So that's why they end up being points of inflection off of the original graph. So -1, 1, and 3. Right, so from here, we want to build the intervals in with concave up and concave down. So now we got to look at something a little differently. We can't quite look at, the curvature. We got to look at more the slope. Okay, look at the slope. That's right. Wherever the slope is increasing, is concave up, because the way we define concave up is slope is becoming more positive. So whenever the slope is becoming more positive, that's enough to end up with a concave up shape, even though it's not the concave up shape that we see, because it's not the original graph. Okay, so I'm going to highlight in green where I see positive slope, which is going to translate to concave up. Concave up is going to be where negative slope is going to occur. Highlight that in orange. Okay, so from -3 to -2, concave up. And from 1 to 3, also concave up. From -1 to 1, concave down. And so same thing from 3 to 4. So we don't want to look at the derivative graph anymore, because we're going to create our visual graph based purely on our sine lines, right? Our sine lines is going to give us a much better picture that's going to match the shape of our graph. Okay, part B is asking for concave up, concave down. That now is easy, right? You can just write out the statements based off of your symbols. Sorry, G. Okay, so part C, we're going to create the shape of our graph, but we're just going to rely on these. Okay, so part C here, we want to sketch our g of x graph. We have some information given, which will kind of help anchor our graph a little bit. So -3, 3, and 4, 6. Let's go ahead and plot those points. Okay, we actually have our starting points here, -3, 3, and 4, 6. Okay, let's just go ahead and sketch out our graph first based off of the arrows. And let's not worry about the concavity until later. Okay, so we know we expect a relative minimum at negative 2.5. So I'm just going to make it more dramatic. I'm going to pick a point lower here. Okay, I'm going to target that point. At 0, I want a relative max. So I'm kind of choose a point. Now, you can choose any point you want, right? As long as your shape looks like mine, all that matters. Target a relative max somewhere here. And then I want a relative min at 2. Make it low here. So I'm going to follow the arrow here. My arrow says to go down until I hit my relative minimum. Relative minimum. After it, my graph is going to rise until it hits 0, a relative max at 0. And then 2. I know there's a relative minimum at 2. And then rises up all the way to 4. This is not the full curvature of the graph, but I don't really care. I just want to get the path of the graph down on paper. Okay, now let's move on to the second derivative sine line. How many points of inflections do you see? Just 2. Remember, a point of inflection is where there's a change in signs on either side, right? So -1 has a change in signs, 1 has a change in sign, and 3 has a change in sign. Now, we don't really know where the points of inflections are. Well, we know in terms of the y values, but we know they land at -1, 1, and 3, right? So it doesn't. So just wherever the graph landed, however way you did it, just go ahead and put a negative, plot that point, right? Highlight that point. Kind of gives you a goal as to where your concavity is going to change. So wherever my graph landed at -1, I'm just going to go ahead and highlight that point. Okay. Wherever the graph landed at 1, I'm going to highlight that point. Wherever your graph landed at 3, I'm going to highlight that point. Okay, it kind of gives me some anchor points because I know I want to have a change in concavity, and it kind of gives me some target points for me to work from. But if yours is lower or higher than mine, it doesn't really matter. Okay. All right, so now we want a concave up. First. So I'm going to target is that first red dot there. I'm going to want that region to be concave up. But then it's going to switch, right? It's going to switch to a what? Concave down. So I'm going to over exaggerate that concave down shape. Give myself a target so I know when I want to switch back over. Concave up again. Finally, concave down, but I don't want to do a full concave down, right? It's because if I do a full concave down, then I'm creating a new path, which is not part of my graph. So I just want to kind of have that concave down, but increasing curvature there. Let's do a part D as well. A part D, where I'm going to ask you to sketch the second derivative graph. So second derivative graph, we're just relying on our concavity sine line. Second derivative sine line. Now, a lot of students want to do this. They want to create curvatures that matches the shape they see here. But right, you just have to understand that we just want the graph to live either above or below the x-axis, depending on. Okay, so here's my second derivative coordinate plane. And I have to kind of label, right? It's my y-axis doesn't represent position. It doesn't represent slope. It now represents concavity. So anything on the x-axis is where my point of reflection is. Anything above is concave up. Anything below is concave down. Okay, so what can I place onto my x-axis? Yeah. I know my graph is going to connect through those dots. Where do I want my graph to live between -3 and -1? Above. So I don't have to make it a weird curvature. I just can have the graph kind of just fall to that point. You know your graph is not going to have as many curves because it's a second derivative function. So each derivative that we take, the degree keeps falling. So as long as we have our graph in that region, okay. So match the location with what you see on the right side. Okay, where do you want the graph between -1 and 1? Below, but it's got to loop back up because there's a point here kind of help guiding us. We know the graph has to connect through all the points. Okay. And then between 1 and 3, above, and then to the right of 3 is below. Let me give you your quizzes back, see if you have any questions. Your background view version. Sure.
The test will be a mix of those type of problems and then, like maybe one of each of the two or,
Optimization.
yeah.
Yeah, yeah.
And
Give you
then
probably 2 optimization, 1 derivative graph, 1 original function graph, and then 1 to 3, 4.
Or on the quiz?
No,
It wasn't.
I'll give it back to you if you want it.
I'll take it during 7th period.
So,
I was surprised. I did much better than expected.
yeah, I mean, you only messed up on that problem.
The MDT. I mean, not the MDT, It was secondary.
secondary test, yeah. Yeah. A lot of students messed up on that, just didn't know what.
I forgot to, split the 4.
Yeah.
We'll see you during set.
Yeah, see you in class. I think that you want to go over.